You know, when you picture Egyptian treasures, you think gold, lapis, but think about Tutankhamun's famous pectoral, that amazing breastplate.
Oh, yes. Stunning piece.
Right. But dead center, there's this bright yellow-green scarab beetle. And it's not, emerald or peridot, it's glass, but natural glass.
That's it. Libyan Desert Glass. And that scarab is maybe the most famous example, but the glass itself.
Mm.
Well, scientists really started taking note around 1932. It's just scattered across this huge area of the Western Desert in Egypt near Libya.
Scattered, like just lying on the sand.
Pretty much.
Right.
Tens of thousands of square kilometers. It's a really enigmatic material. There's just so much of it.
And I guess the immediate puzzle was, where did it come from? How does glass just appear in the desert?
Exactly. Right from the start, that was the question. It looks melted, sure, but melted by what? Was it volcanoes? Something weirder. People have been debating it for, gosh, nearly a century now.
It sounds like it has features that point one way, but maybe other things that just didn't quite add up.
Precisely. It screams high temperature, no doubt about that.
Mm-hmm.
But fitting it into a neat geological box, that was tricky. It's been a real scientific head-scratcher.
So that's our mission for this deep dive, right? To look at the sources, the science, the history, and especially these recent breakthroughs that might finally be cracking the case of Libyan Desert Glass.
Oh, yeah, it's a fantastic story. It links, ancient pharaohs and their jewelry directly to super high-tech lab analysis happening today.
Cool. So we'll look at what it is, why it was so puzzling, the clues hidden inside it, and this new evidence.
Absolutely. We'll cover its weird properties, the microscopic clues, the sort of smoking gun evidence that emerged. And yeah, we also have to talk about the big piece that's still kind of missing.
All right, let's start simple. What is Libyan Desert Glass? If I picked up a piece, what would I be holding?
Okay, so physically, it's usually these irregular chunks or shards, not like smooth river pebbles. The color is typically clear to pale yellow, but sometimes you get this really vibrant, almost canary yellow, like King Tut scarab.
Ah.
And the really striking thing is its composition. It's almost pure silica glass, like 98% SiO2. That's exceptionally pure for something natural.
98%, wow.
Yeah, and it's mostly free of crystals, not many bubbles compared to, say, obsidian, which is volcanic glass.
Okay, so that purity and the lack of crystals, does that immediately tell scientists something about how it formed, like conditions?
Oh, definitely. It tells you two key things. One, extremely high temperatures, hot enough to completely melt the source rock, leaving almost pure silica behind. And two, very, very rapid cooling. That fast cooling is what stopped crystals from growing, leaving it as glass. You can sometimes even see like flow lines or layers inside, showing it was molten and moving.
And you said it's scattered, not just a few pieces here and there.
Not at all. The area, the strewn field, as they call it, is massive. Estimates are around 6,500 square kilometers. Just imagine that.
That's huge. And the quantity.
The numbers are kind of mind-boggling. Potentially up to 100,000 tons of this glass just lying out there.
Whoa, 100,000 tons. That is a lot of glass. Do we know when this happened?
We do, roughly. Radiometric dating places the formation event around 29 million years ago.
Uh-huh.
So, yeah, deep time.
Okay, 29 million years ago, a massive field of super pure, high-temperature natural glass. My mind immediately goes to tektites.
Exactly. And that's where the whole debate really kicked off for decades. Tektites fit that general description, right? They're natural glasses formed when a meteorite hits the Earth.
Right. The impact melts rock, splashes it up, and it cools into glass as it falls back down.
Precisely. So you get natural glass foamed hot, cooled fast, scattered over a wide area strewn field. Libyan Desert Glass ticks all those boxes, superficially at least.
Superficially. So why wasn't it just classified as a tektite straight away? What caused the doubt?
Well, there were some pretty significant sticking points. First, that composition. 98% silica is way purer than most tektites. Tektites usually reflect the composition of the impact site rock more closely, often with more iron, aluminum, things like that.
Okay. So the chemistry was weird for a tektite.
Yeah, unusually pure. Second, the internal structure. While it shows it was molten, it didn't always show the classic microscopic features you see in many tektites. Things like distinct little strings of melted quartz called Licia tellurite, or really pronounced flow patterns called schlerin. They weren't obviously jumping out in the main body of the glass in early studies.
Some internal textures maybe not quite right. What else?
Oh, the sheer amount. That 100,000 tons figure. That's potentially 100 times more glass than you find in many other known tektite fields. The scale was just immense.
Okay, that's a big difference.
And the absolute killer for the simple impact theory, for a long time, was the missing crater. If you have a tektite field this big, you expect a corresponding impact crater somewhere nearby.
And they couldn't find one.
They looked. People proposed candidates based on satellite photos, like the Kubera structure. But when teams went there on the ground, the geology didn't match up with an impact crater. No definitive impact scar.
Right, no crater. It makes the impact idea harder to swallow, I guess.
Exactly. So, with a weird chemistry, the slightly different texture, the huge volume, and no obvious crater, well, scientists had to consider other possibilities. For decades, people floated ideas like maybe a massive volcanic steam explosion, a hydrovolcanic event, or even a huge explosion in the air, an airburst. Like, think Tunguska, but maybe vastly bigger. An object exploding violently in the atmosphere could generate immense heat and scatter debris without leaving a traditional crater.
So maybe it didn't actually hit the ground.
That was one idea seriously considered, to explain the glass without a crater and maybe account for the different properties. It kept the origin story really murky for a long time. Features suggesting impact, but key pieces missing or contradictory.
But you mentioned clues inside the glass, the inclusions.
Yes, exactly. Like tiny time capsules, just like flaws in a diamond, tell its story. The microscopic stuff trapped inside the Libyan Desert Glass held the real secrets.
What kind of stuff are we talking about? Beyond just bubbles.
Well, yeah, besides the gas bubbles and those flow lines, you sometimes find tiny spheres or snowballs of cristobalite that's a form of silica that only forms at high temperatures.
Okay, so more evidence for heat.
Definitely. And early studies also found other microscopic high-temperature indicators. Things like Le Chatellierite, basically melted quartz grains, and baddelite, which is what zircon turns into when it gets superheated. Finding these definitely pointed towards an extremely hot event, consistent with impact or a massive airburst.
So heat was clear. Did they find anything pointing specifically towards space? Towards a meteorite?
They did, yeah. Chemical analysis started giving hints. In some samples, especially in darker streaks or bands within the glass, they found higher levels of elements like cobalt, nickel, and iridium.
Ah, elements that are more common in meteorites than Earth's crust.
Exactly. And even more tellingly, isotopic studies looking at the ratios of rhenium and osmium isotopes within those dark bands strongly suggested a cosmic component, material that had to have come from space mixed in.
Okay, so now we have high heat and traces of extraterrestrial material mixed in. That really strengthens the impact idea, doesn't it?
It does. It makes a purely terrestrial origin like volcanism much less likely. But it still didn't absolutely rule out a massive airburst, which could also involve meteorite fragments mixing with melted ground material. The missing piece was still definitive proof of shock.
Shock, meaning the intense pressure wave from an impact?
Precisely. Extreme heat you can get other ways. But the kind of ultra-high-pressure shock wave you get from a hypervelocity impact leaves unique fingerprints in minerals. The question was, could they find that fingerprint inside the Libyan Desert Glass?
And this is where the newer high-tech analysis comes in.
This is the breakthrough. Using really powerful microscopes and analytical techniques, things looking at the nanoscale structure, scientists focused on tiny grains of zircon trapped inside the glass.
Zircon again. Why zircon? I know it's tough, used in dating rugs.
Exactly. Zircon, ZrSiO4, is super durable, but it also transforms in very specific ways under extreme conditions. It's like a tiny, tough witness that records pressure. They use things like transmission electron microscopy, TEM, to see structures almost down to atoms, and electron backscatter diffraction, EBSD, to map crystal orientations.
So peering deep inside these tiny trapped zircon grains, what do they find?
They found something amazing. In some zircon grains, they observed these microscopic arrangements. Tiny new zircon crystals called neoblasts that had formed within the original grain. And these neoblasts weren't random. They were aligned in a very specific systematic pattern.
A pattern? What kind of pattern?
A pattern showing consistent 90-degree relationships between the orientations of these tiny crystals, specifically along certain crystallographic directions. It sounds technical, but this precise geometric arrangement is unique.
Okay, 90-degree relationships. Why is that significant?
Because that specific pattern is the telltale signature left behind by a mineral called rhyodite. Rhyodite is a high-pressure version, a polymorph, of zircon. And it only forms under the immense shock pressures, we're talking gigapascals, of pressure generated by a meteorite impact.
Only from impact pressure.
Only impact. Rhyodite itself isn't stable at surface pressures, so it eventually changes back to regular zircon. But it leaves behind this unmistakable nanostructure, this specific 90-degree pattern among the neoblasts. Scientists even have a name for it: former rhyodite in granular neoblastic zircon, or phrygene zircon. Finding phrygene is like finding the impact's fingerprint.
Wow. So finding that phrygene structure inside zircon grains, which were themselves inside the Libyan Desert Glass, that's direct proof the material experienced impact shock pressures.
That's it precisely. It was the first undeniable evidence of high-pressure shock deformation within the LDG itself. They also found other nanoscale evidence, like tiny inclusions of a specific high-pressure form of zirconium dioxide, ZrO2, called orthorhombic OII, which points to pressures above 13.5 gigapascals.
13.5. That's enormous pressure.
Over 135,000 times the air pressure around us right now. You just don't get that from volcanism or even a massive airburst. You need a solid object hitting the ground at cosmic speeds.
So the rhyodite signature and these other high-pressure minerals, that pretty much settles the origin question then. It was an impact.
It's now the overwhelming consensus, yes. It provides the direct evidence of hypervelocity impact that was missing for so long. It effectively rules out things like air bursts or hydrovolcanism being the sole cause. The pressure evidence is key. And these studies also confirmed the crazy temperatures involved, melt temperatures likely exceeding 2,750 degrees Celsius, almost boiling the silica.
Incredible. Such tiny details, solving such a huge puzzle. But, okay, if it was definitely an impact, what about the crater? We still don't know where it is.
And that remains the big, lingering question mark. The final piece of the puzzle is still missing. The glass tells us how it formed impact, but not exactly where.
What happened with that Kibera structure idea? You said ground studies didn't support it.
Right. It looked promising from space, but fieldwork showed problems. The supposed central peak area, it had layers of sandstone lying perfectly flat, totally undisturbed. An impact's central uplift would be a mess of folded, shattered rock.
Not exactly impact evidence, then.
Not at all. Plus, detailed chemical and isotopic fingerprinting compared the Kibera sandstone to the LDG, and they didn't match. That sandstone wasn't the source material for the glass.
So Kibera's out. Where does that leave the search?
It leaves it ongoing. We have incredibly strong evidence now, written in the glass itself, that a high-pressure impact event created it 29 million years ago. But the actual impact site, well, maybe the crater is buried incredibly deep under shifting sands. Maybe it was heavily eroded over millions of years. Or maybe, just maybe, the impact dynamics were unusual, perhaps a very low-angle hit, or something that fragmented just before impact, creating the glass field without leaving a classic, easily recognizable crater structure. The desert keeps its secrets well.
It's wild to think we have definitive proof from nanostructures, but the giant hole in the ground is still elusive. So what about Libyan Desert Glass today? Obviously, the Tutankhamun connection gives it historical weight.
Oh, hugely. It remains this really desirable, fascinating material. You've got the beauty, the strange purity, the incredible scientific story of its cosmic origin, and that direct link back to ancient Egypt. It makes it prized by collectors, researchers, gem cutters. It's a tangible piece of a truly cataclysmic event.
And I imagine, like many desirable gems or materials, people try to fake it. How can you be sure you have the real deal?
Yeah, imitations are definitely out there, usually just yellowish man-made glass. And telling them apart isn't always simple with basic tests. For instance, a simple Raman spectrum might look similar because both are mainly silica glass. But there are more specific techniques. Real LDG has a distinctive feature in its near-infrared spectrum, a little peak around 5,200 inverse centimeters that fakes don't have. And detailed chemical analysis, like using an electron microprobe, can spot the difference. Real LDG is incredibly low in elements like iron compared to typical man-made glass. So its unique purity is also a key identifier.
So even telling real from fake today relies on understanding those specific scientific details about its formation and composition.
Absolutely. The science behind its origin story is directly tied to how we authenticate it now.
What an amazing journey this has been. We started with, a mysterious yellow gem in a pharaoh's necklace and this baffling glass scattered across the desert, and ended up finding definitive proof of a massive meteor impact locked away in the nanostructure of tiny mineral grains inside that glass.
It really highlights how science progresses, doesn't it? Decades of debate, different theories, and then new technology allows us to see details nobody could see before, and suddenly the picture becomes much clearer. It's a great blend of geology, history, and cutting-edge material science.
It really is. And it leaves you thinking, how incredible is it that the key to understanding this colossal ancient impact event that melted rock and flung glass across Egypt was hidden in plain sight, but only visible at the nanoscale? We found the impact's signature, but the desert still hides the scar. Makes you wonder, what other immense stories are locked away in the tiniest details around us, just waiting for us to find the right way to look?
If you wish to hear more